All right, so we're back. We're going to try to do problems 4, 5, and 6 in this video. So this is one of the ones that most people got wrong on this exam. And I'm not exactly sure why, but there are a number of possible complications, so I'll run through a number of them. So the question is your molecule polar or nonpolar? And then if it's polar, draw the polarity arrow. So I'll just tell you right now, all of the molecules that you should have drawn for this should have been polar. So your molecule definitely should have been polar. So what are the two criteria to find a polar molecule? Number one, there has to be at least one bond with a difference in electronegativity greater than 0.3. Some people say 0.4. I usually like to say 0.3 with the caveat not carbon-hydrogen bonds. And I could go off on a rant about that. I think our periodic tables are printed with the wrong electronegativity for hydrogen, which makes that confusing. But I'll leave it at that. So anyway, step number 2, they have to have an unbalanced shape. And unbalanced just means that they're not exactly equal each other on opposite sides. So, for example, some examples of balanced that we could see would be something like carbon dioxide, when you have a linear shape and there's an oxygen exactly opposite each other in there. Or something like carbon tetrachloride, where you have carbon with 4 chlorines evenly spaced around it. So these ones are pretty easy to see. There's just one atom in the middle and they're evenly balanced around. So those are balanced. So we're looking for something that's unbalanced. And the key thing here is back to what we were talking about before, where you can rotate these molecules around. So how do you know if it's balanced? If it can rotate into something that looks somewhat balanced and then rotate out of something that looks balanced? Well, that's not balanced. That's the basic idea here. And I think that's one of the biggest confusing points for people when they did this one, is that a molecule might look somewhat balanced in the way you drew it, but if that's only one way that molecule can rotate. It can flop itself around in lots of different conformations. Like, for example, if I was holding 2 pens out in my hands, well, that might be balanced, but what if I just put 2 pens over here in one hand? Or if I held them both together on one side of my body instead of holding them out on opposite sides of my body? Then I become balanced differently, right? So, for example, I'm holding them, imagine I got my arms stretched out and they're on either side of my body versus holding them together in front of my body. I'm balanced differently. And that's the same thing with these. In some arrangements, you might think that those looked like I drew them. I could redraw this molecule up here in a way that sort of looked like bromine and fluorine might be opposite each other. Between bromine and fluorine, there's 1, 2, 3 carbons. So I could go 1, 2, 1, 2, 3 carbons, put a fluorine bonding off this end, put a bromine bonding on this end, and 2 carbons then coming off the middle. This molecule looks somewhat balanced now. It's the same molecule. I've just rotated my viewpoint on it, rotated the bonds around a little bit. And especially if they were both fluorines or both bromines, you might want to say that's balanced. But remember, it can rotate through all of these different arrangements. And if it's unbalanced in any of the arrangements, it's unbalanced. So all of your molecules actually meet these criteria, because between the element and carbon, they should have a big enough difference in electronegativity. And then they should then be able to have an unbalanced shape. So in organic chemistry, we actually don't even really need to think about this anymore. You can sort of ditch this electronegativity thing, and you can even supersede most of this, is that we can actually answer most of these questions if does it have oxygen, nitrogen, or a halogen, then there's a really good bet it's going to be polar, with just a couple of exceptions. One of those is right here. And I'll get to another exception in a second. But that's basically it. If it has oxygen, nitrogen, or halogen, and it's not something like completely evenly distributed around one carbon or around all of the carbons in the structure, then you're looking at polar. For most molecules that we'll look at, that'll be the way it works. So then the polarity arrow, people did actually seem to know how to do that. If I were drawing a polarity arrow on these molecules here, definitely if you're trying to draw the one, you can draw individual bond polarity arrows, or you can draw the one for the whole molecule. I accepted either on this question for the most part. But what I was asking you for specifically was the whole molecule polarity arrow. If you had just put polarity arrows on fluorine and bromine, I may have accepted that as well, depending on the context. But what I would have looked for here is fluorine is by far the most electronegative of the two. I would have put a polarity arrow toward fluorine. It could have gone that way, or it could have gone this way, as long as you had it one or two pointing toward fluorine on the molecule. That would have been fantastic. You could have even put it right through the middle of the molecule like this, pointing toward both halogens. That would have been acceptable as well. Really, anything in that category would have been great. All right, so one other little exception to this that we were talking about would be if you had a trans bond, like if you had a double bond and you had, some more carbon chain over here and some more carbon chain over here, but on these sides you had something like a fluorine and fluorine. So that would essentially act as nonpolar. And I hope you can see the difference, because we've been talking about it along the way, that these can flop around into any arrangement they want because they have single bonds. They're alkanes. So they can rotate into any one of those conformations they want. But this, because of the double bond, is locked into place. So the fluorines have to stay opposite each other in this particular structure. So then you can go with something like nonpolar for that. It would be reasonable to call this nonpolar at this point. So that's pretty much it. For polar, they should have all been polar. You could have actually just known that by saying, hey, if it has an oxygen, a nitrogen, or a halogen in an alkane, then it's going to be polar. Or you could go back to the old reasoning as well. So moving on, let's get to question number 5 and 6. I think we can buzz through those pretty quickly. 5 was one that, again, I think pretty much everybody did correctly. It was really straightforward. You just had to take that previous molecule and make a double bond somewhere in it. So you could have drawn any of those representations. I'll draw this one. And basically just add a double bond anywhere you wanted here. And that makes it an alkene based on that. And really the purpose of that was so that to see that you knew what an alkene was. And then also you needed something to use to answer this question that would have different hybridization on the carbons. So then a lot of people, you could go about this a different way. And I think I actually just drew that wrong. So I realize I would have gotten this question wrong. I don't know if you saw when I was drawing. Let's fix it. That I removed one of the carbons. So there would have been a... I'm sorry. I was correct. 1, 2, 3, 4, 5 carbons, bromine, fluorine. Okay, I just got confused. It's correct. So moving on. If we label this, and this won't be for naming yet, but if we just label this 1, 2, 3, 4, and 5, then you could talk about each carbon, carbon number 1, carbon number 2, carbon number 3, 4, and 5. So 1 and 2 are double bonded carbons, carbon with a double bond. So those would be sp2 hybridization. The other ones, 3, 4, 5, are all ones with all single bonds. So that's sp3 hybridization. And then the biggest mistake on this by far was people forgetting to do both and shape. So the shape then of any sp2 carbon is trigonal planar. And I would have accepted just planar, but I think everybody said trigonal planar. And the shape around an sp3 carbon is tetrahedral. These are actually just ways to say the same thing. This is from the Vesper theory, and this is from valence bond theory. Ways to essentially say the same thing about a carbon. This describes what its shape is. This describes what orbitals it's using to bond with. But they both really describe the same type of an atom. All right, so thanks for hanging with me. Come back next time for questions 7 and 8.